Hello and welcome to the problem of the day for June 2nd. This is going to be problem number 2101, Detonate the maximum bombs. I actually thought this problem was a really good problem. It definitely tests your data structures and algorithms, and also it's pretty straightforward, it's not too tricky, and definitely gets you thinking. So let's read this problem. You're given a list of bombs. The range of a bomb is defined as the area where the effect can be felt. The area is the shape of the circle with the center as the location of the bomb. The bombs are represented by zero-index 2D array bombs where bombs I, X, I, Y, I, R, I, and X and Y show the X and Y coordinate of the location of the bomb, where R detonates or denotes the radius of the range. So for example, for this right bomb, X and Y would be right over here, right, which would be x6, y1, and the radius is 4. So given a list of bombs, or you may choose to detonate a single bomb, and when it's detonated, it will detonate all bombs that lie in its range. These bombs will farther detonate the bombs that lie in its range. Given a list of bombs, return the maximum number of bombs that can be detonated if you're allowed to detonate only one bomb. So let's look at the example. So we have two bombs here. And it says the above figure shows the positions and ranges of two bombs. If we detonate the left bomb, the right bomb will not be affected. But if we detonate the right bomb, both bombs will be detonated. So the maximum bombs that can be detonated is max 1, 2 is 2. And so what you can see in the picture is when the left bomb detonates, in order to detonate the other bomb, the location of the bomb is actually this point. And so when a bomb detonates, that point has to be within its area for it to detonate that one. So when the left one detonates, the radius isn't big enough to detonate the right bomb. But when the right bomb detonates, its radius is big enough to detonate the left bomb. And let's look at the next example. So we have two more bombs. Now we can see that the location of either bomb isn't in its radius. So that's just a 0. Or sorry, that would be a 1, right? Because we are detonating one bomb, but when it detonates, it doesn't detonate anymore. Okay. And here, they're saying the best bomb to detonate is bomb 0 because bomb 0 detonates bomb 1 and bomb 2. So this bomb 1 and bomb 2 is actually this like purple and blue one, and then one of these other, I think bomb 2 or something, detonates bomb 3 or bomb 4. Yeah, bomb 2 detonates bomb 3, which is kind of hard to see, and then bomb 3 detonates bomb 4. So you kind of get the idea. We can't just simply detonate, like let's say we have one bomb, right? We can't just look how many bombs does that bomb detonate, because that bomb detonates more bombs. So if there's another bomb, and then like something like this, right? Well, this bomb will detonate this bomb will detonate this bomb will detonate this bomb will detonate this bomb. And so when we detonate a bomb, what does that mean? Well, actually what it means is we have to check what bombs does that bomb detonate, aka what bombs is it connected to, right? So we detonate a bomb, and instead of this, let's just say any bomb it's connected to, and by connected to, we're going to figure out what the connection means. So we're going to need to check every single bomb that bomb is connected to, and then every single bomb that those bombs are connected to. And so what does this look like to you? Well, surprise, surprise, it looks like a graph problem, right? You have some nodes, and then they're connected to other nodes, and so we're doing a traversal from one node to every single node it's connected to, and then every single node, and then we can just simply figure out how many nodes did we traverse, and that's going to be the number of bombs detonated. We could do that for every single starting bomb, and we could figure out a maximum. So now the other tricky part is, well, how do we figure out how are bombs connected? Like, let's look at some picture, right? Let's just say, first of all, so we know that when let's just think of the bombs as points. So let's think there's a point, just easy example for now. So let's say this is 4, this is 4. First bomb is over here. Second bomb is over here on 4, 4. So 0, 0, and 4, 4. Well, we have to figure out, how do we figure out they're connected? Well, first of all, for a bomb to detonate another bomb, remember, it's like the area of the bomb has to encapsulate the other bomb. So this left bomb, in order for it to detonate the right bomb, this point has to be somewhere in its area, right? Somewhere in its area. And so how do we figure that out? Well, when you have a circle, and you have some points that are connected, what is the farthest that circle can go to connect another point? Well, let's just draw a line. And what does this line represent? Well, it represents its radius, right? So the farthest that bomb can detonate compared to some other point is radius distance, right? And so we have a radius. Now we also need to figure out what is this distance. And if this distance right here is the radius or smaller, then the first bomb detonates the other bomb, and that would look like this. Let's say it exactly equals the radius. Then that point would lie right outside the circle, right? Obviously my picture's kind of bad, but you could see that this point, if r equals d here, where d is the distance between the 2 points, then the bomb is just barely detonating. And then if r is less than d, so if the radius of the circle is less than the bomb, is this d? So if this is r and this is d, so d is this whole thing, right? This whole thing. Then we can see that we won't detonate. But then if r is greater than d, that means that second point is in the circle, and so that detonates for sure. So now this is d, and this whole thing is r. And so all we have to do for 2 points to know if one will detonate the other, and by one detonating the other, we can also say there's an edge from one to the other, right? So there's an edge from one to the other, and then we can just simply check, well, what other points does that connect to, by also checking the distances in the radius. So that's what we need to do. We need to get the distance between each 2 points, and then we need to figure out, is that distance less than or equal to the radius of the bomb that's blowing up, right? So let's say this bomb, and then you need to do it both ways. So for some directed graph questions, you can simply, like, if you have a left and a right, for some graph questions, also this is directed, right? So directed means this is not the same as this, right? So that is not the same as that. So you will have to check both ways, right? You'll have to try to detonate bomb 1, see if it reaches bomb 2, and then you have to detonate bomb 2 and see if it reaches bomb 1 in this question. But anyway, how do we figure out this distance? Well, so for math, this distance between one point and the other point, if you take a look, no matter where you have 2 points, if you just draw a straight line and then you draw a line along the x-axis and the y-axis, that becomes a right triangle, right? And so what's the distance here? Well, it's the hypotenuse. And what's the hypotenuse? It's Pythagorean theorem, right? So this is a squared, b squared, c squared. Same here, right? So this point is, let's just say a is the x distance, b is the y distance, and this is c. So then c squared is going to be, right, from Pythagorean's theorem, it's going to be this. So you do have to know that for this question. And so a squared is the distance between the x values. So let's just say that, so the distance between the x values is actually going to be what? It's going to be x2 minus x1. And this is technically the absolute value, but we're going to actually square it, so it doesn't matter, right? So squared plus, and then b is the difference between the y values, right? So y2 minus y1 for the 2 bombs. Once again, we're going to square it, so it doesn't matter, equals c squared. And now how do we get this actual c? Well, c is going to be the square root here. So you do definitely need to know some math for this problem, which is kind of rare for a LeetCode problem. But, you know, so this is the distance formula for distance between 2 points. It's going to be x squared, x2 minus x1 squared plus y2 minus y1 squared. And we're given those points, right? So if we have a point like 0, 0, and 4, 4, what would the distance be there, right? So it's going to be the square root of, let's just say this is 2. So that's just going to be the square root of 4 minus 0 squared plus 4 minus 0 squared, right? And that's how we would get c. And we can even test this for the really easy problem. So let's just do that. So let's just delete this. Let's test this for this initial one. So we have a point, just say it is 6, 1. And then once again, it doesn't matter which order you do this, and it's going to be the same because you're squaring them. So then we have 2, 1. So what's going to be the distance there? Well, you can actually tell here it's 4 units away, but let's try our formula, right? So we'll call this the second one, and we'll call this the first one. So remember, it is x2 minus x1, so that's going to be 2 minus 6 squared plus, and then y2 minus y1, they're the same, so 1 minus 1 squared. So clearly this is going to be the square root of negative 4 squared, which is square root of 16, which is 4. And you can see that. So if if one of these two values is the same, then the distance is just the difference between the x and y values, or the difference between the x values. But we can see that our formula works. So let's say once we do get our formula, well, now it's pretty straightforward, right? All we have to do, now that we know what a path looks like, a path is the distance smaller than the radius of the bomb we're blowing up. So once we have some nodes with paths, and like let's say we blow up one bomb and it has some paths and so on, you know, there can be whatever paths, and there might be loops and things. So now we have to just traverse down every single node until we can't get to anywhere else. So right, so we'd blow this one up. We can do like a DFS. So we'd go over here, we'd go over here, we'd go over here, we'd go over here. So we would try to go to every single node possible. We would have some kind of counter there. And then we'd figure out, okay, starting at this node, this is how many we can blow up. And we just try that for every single starting node. Okay, and that's pretty much all of the, you know, prep work for this problem. So let's try to code it up now. So we do need a couple things for this. We need a visited set, right? Just to make sure we don't visit the same node twice when we do our DFS. So let's do that. Then we also need a res. Let's just say that's 0. And we also need something like a cur count. And that's going to be the current count of the nodes we visited. So we're going to have to reset that at every starting node, right? Like, let's say we start at this node. We're going to have to count the nodes we visited. Then we're going to start at this node, count the nodes we visited, and so on. Okay, so that. Now we need to also have a dictionary to actually make these paths, right? Because we're just given a list of bombs. We need to make a list of paths from bomb to bomb. So we need to actually make these connections. So paths equals default dict, and it's going to be a list. So every node is going to have a list of nodes that it's connected to, and then we're just going to traverse that. So let's say we're at some node 1, it'll have a list of some other nodes that you can go to. Let's say you can go to 2, 3, whatever. And we're just going to say, did we visit? We're going to go through all of them. Did we visit here? Okay, if we didn't go there. Did we visit here? If not, go there, and so on. So it's pretty straightforward. So now we have to actually loop through our bombs and calculate these distances. So it's going to be a nested for loop, because remember, we have to compare every bomb to every other bomb. And also, yeah, and then so let's just do that. So for I in range, length bombs, right? And then same thing in j in range, length bombs. So we could say if I equals to j, don't just continue or something, but we're going to take care of that with a visited set, I think, so it's not really going to matter. So even though a bomb is going to be, or actually let's just get rid of it just in case. So let's just say if I equals j, let's just continue, right? Because we don't want to see the distance between, if the index is the same, we're seeing the distance between the same bomb and itself. So we want to compare every bomb to every other bomb. Okay. So now we have to actually calculate this distance. So that's going to be, remember, square root. I think it's math.square root, but I think the math is imported in here. So, and then what's that going to be, right? So it's going to be, so let's say j is the 2 value and I is the 1 value here. So it's going to be the square root of bombs j 1 or 0 minus bombs I 0. So these are the two x values, then we need to square those, right? Squared. And then we need to add the other one. We can just copy this. So now it's the y values. Okay. There we go. Now we need to say, okay, so this actually needs to be, no, this is fine. Okay. Yeah, so that's fine. Now we need to say check, is the distance less than or equal to the radius of the current bomb? And our current bomb is going to be the I value, because we're going to be comparing the left to the right. So we'll just say the current bomb is this. Okay, so if distance is less than or equal to, and then that's going to be bombs I, and then the radius is the third value in the subarray. So that's going to be 2. Then we need to add it to the paths of that bomb, right? So paths, bombs I, path bombs I. Actually, no. Sorry, this shouldn't be path bombs I. So with these paths, we're just gonna have the indices in the bombs array, right? So like if this is bomb 1 and bomb 0 or so on in this bombs array, it's just gonna be in C. So we don't need the bombs. We just need the I and the j. So dot pen j. Okay, now I'll just print this just to see if we Got that correct. Okay. As usual. List has no, can't spell anything. And we do need to have a return value, I think, otherwise it's going to give us some problems. So let's take a look. Okay, so we can see that so you can go from bomb 1 to bomb 0, which is what they want here, right? So that's correct. And let's just maybe check some other test cases. So yeah, so in the second test case, the bombs aren't connected at all, so that's fine. Now we could see that from 0 detonates bomb 1 and bomb 2, that's what we wanted. 2 detonates bomb 1 and bomb 3, 3 detonates bomb 1, 2, and 4, and 2 detonates. Yes, I think that's correct. Okay, so now that we have that correct, now let's move on to the next part so we can get rid of this return value. So now we need to remember, we need to have a DFS function, so let's do that. So def DFS, and what we're going to be passing into a DFS is just an index. And then it's pretty straightforward. So we're only going to be going into this DFS in non-visited nodes. So what we need to do is we need to add it to the visited set, right? So we need to add it to the visited set. Then we also need to increment this cur count value. Okay, and then we need to increment that. Now we just need to iterate through the list of nodes in its path, meaning the nodes that it can go to, and we need to see if they aren't in the visited set, then just DFS to those, right? So for path in paths index, if path not in visited, DFS path. Okay, I think that's all for the DFS. Now we need to actually loop through our entire list of nodes in the bomb to try every single starting node. So that's going to be for I in range length bombs. So what do we need to do in these? We need to clear the visited set, right? Because we're doing a brand new, we're starting over from the first one. So we need to do that. We also need to reset the cur count. Okay, now we need to call DFS on the node we're at. So and then we need to, so we'll have some cur count at the end here, and then we need to check, okay, how many nodes did we visit? And then we need to try to maximize that, right? So that's going to be res equals max res cur count. That's how many nodes we visited from the node that we started. Now we just need to return res here, and that's our maximum total bombs we could blow up. Okay, perfect. Okay, so that's good. Now let's think of the time and space complexity. So hopefully that makes sense. There's not too much you can do to optimize this, and also, once again, you can see that, as usual, you can make this function, you know, not super optimal because there's only 100 bombs. So that's another hint if you wanted to, like, think of some algorithms that, like, it doesn't have to be super efficient because there's only 100 bombs. It's not like 10 to the 6 or 10 to the 8 bombs or something. Okay, so let's think of the time and space complexity here. Okay, so what are we doing? So this is going to be, obviously, big O of n squared, right? We're comparing every bomb to every other bomb, so that's already that. Now let's think of some other stuff. Okay, so our DFS is going to visit every single node that hasn't been visited. So that's worst case big O of n, right? We're going to go through every single node, but we're only going to visit one node one time. But yeah, we can technically, worst case scenario, we can visit every single node. And so from every single starting node, we can visit every single node. So I believe this is, like, these two combined are also going to be big O of n squared. Now, so from every single node, we can visit every single node, but I think actually another problem is, so for every single node, we can visit every node, and then also for every single node, I think we do have to check the path. And so if every node was connected to every other node, let's say we would start at, like, the first node, we can DFS to every node, and then at every node we have to also check this path, and this path would be every node. So this for loop would technically take n nodes as well. So I think this might actually be n cubed, because we have this for loop, that's big O of n, we have this DFS, that's big O of n, and then in the DFS we have to check, yeah, we don't DFS to other nodes, but we still have to do this for loop. So it's a worst case scenario, it's a for loop and another for loop and another for loop. So I think it's actually big O of n cubed for time. I could be wrong, but I think that's right. And then for space, well, what do we have? We have a visited We have a visited set, which could be, that's just big O of n. We can only visit each index one time. We do have this paths thing. And so if every node was connected to every other node, then that would be, so let's think, if every node is connected to every other node, I think that would be big O of n squared, because for the key, you'd have every node, and then you'd have a list of every node as well. So that would be kind of like a nested for loop. Okay, and DFS max depth would be n if you started at the first node, so that doesn't, yeah, so I think it's this, because, yeah, so for our dictionary, so I'll just show you this, right? Let's say every node is connected to every other node, and we have 4 nodes, then it would be something like this. For 0, you'd have 1, 2, 3, you know, for 1, you'd have 0, 2, 3, and so on, and so you'd have n keys, and each node would have n values, so then the total space would be n squared. Okay, so hopefully that's straightforward enough. So I think this is it. Someone can correct me if I'm wrong for time and space complexity. But yeah, that's it for this problem. I thought it was a pretty good problem, not too hard, but definitely got you thinking. And so if you like these kinds of problems and if you like my explanation, please like and subscribe. It really helps grow the channel. And I'll see you in the next video.